Good morning once again, everybody.
Good morning, sir.
Today I would like to introduce our tutor, our speaker for the class. And before I speak on, let me introduce myself first. My name is Dr. Timothy. I am an academic staff of Osun State University, Osogbo, Nigeria. I'm also the founder of Osun R User Group, Nigeria, and also the coordinator of Team R Programming Consults, Nigeria. Today, we have invited a renowned professor of applied statistics and econometrics in person of Professor Maureen Tobechukwu Nwakuya. He's a professor in the Department of Statistics, University of Port Harcourt in Nigeria. Having gotten a profile, Professor Tobechukwu is a member of a Chartered Institute of Statisticians of Nigeria, (CISON). Her expertise includes statistical learning, econometrics, medical statistics, explainable AI, and machine learning. She has more than 80 years of teaching and research experience. She's very strong in statistical modeling and econometric analysis. She promotes statistical literacy via workshop and webinar. One of them is what we are having at the moment. She leads funded research, publishes in high-impact journals. Equally, she is the coordinator of Uniport's Laboratory for Interdisciplinary Statistical Analysis, Uniport LASER. At long run, I will introduce to you our professor of statistics on behalf of Art Consortium and Art Foundation, as well as on behalf of the Osun R User Group. I would like to introduce to you our professor for talking to us today on the topic, Beyond Regression, Harnessing Explainable AI for Machine Learning Prediction. Professor, please come on board. You have the floor. Thank you.
Yeah, thank you very much, Dr. Tim. I'm honored to be here. So I want to thank everybody for finding the time to join us this morning. So
how much?
As you well introduced me, I'm actually from the University of Port Harcourt, Department of Mathematics and Statistics. So I would like to share my slide now. So permit me to share my slide.
Please, you have the permission. You are a co-host, so you can share your slide.
Okay, so today we are going to be talking on Beyond Regression, Harnessing Explainable AI for Machine Learning Predictions. And our contents today, the first thing we are going to look at is the roadmap, then the contrast, and then explainable AI. What we're going to be taking home today will be that you will have an understanding of predictive modeling beyond the traditional or classical regression. You'll be able to understand how to implement and evaluate machine learning models like the random forest, the SVM, support vector machine, the SGBus, and the machine learning logistic regression for the purpose of classification. In machine learning, you have supervised and unsupervised learning, and under supervised learning, we have classification and regression. So today, we are focusing on the classification. You will also understand model evaluation techniques like the confusion matrices for classification performance and other performance metrics. We'll also gain insight into feature importance, like identifying which feature most influences the predictions. You will as well gain insight into explainable AI with Dallas and Sharp, and also using the values from both to understand individual predictions and visualizing feature effects to interpret model decisions. You experience hands-on, you have experience with hands-on with R packages like the Dallas and the Sharp, the ML Bench, Carrot, and others. And then you have the ability to replicate the workflow, okay, for your own data set. The roadmap, where we are coming from. We are coming from the classical regression thinking. In classical regression, like the linear regression, the goal is to understand the relationship between variables, okay? Typically, what we do is we specify a model, like a linear relationship. We estimate the parameters, like the coefficients of the model. We interpret the results. For example, we can be able to say if X increases by 1 unit, Y increases by the coefficient beta of any of the X's, depending on the one you're looking at. Okay. Regression, the classical regression focuses on interpretation and inference. So regression basically answers questions like which variable matters? How do they influence the outcome? Is the effect significant? Is it statistically significant? So we can say that regression sums up to be explanation and understanding relationships. Okay, now where are we going to? We are going to the machine learning thinking. Machine learning shifts the goal slightly. In order, it helps us to make the most accurate predictions possible. In machine learning models, the models basically learn the patterns directly from the data. They capture the complexity of the data, both the linear and the nonlinear relationships, and it basically focuses on performance, like the accuracy, the precision, the AUC, and the likes. So today we are going to look at the random forest, the SVM, the SGBus, and then the machine learning logistic regression. So what machine learning does is it tries to find out how well we can predict unseen data. So machine learning is about prediction and optimizing performances. Okay, so it's like both of them, between machine learning and the classical regression, is like a trade-off of accuracy and interpretability. Regression, the classical regression gives us interpretability. Machine learning gives us accuracy. But machine learning has gone beyond that. Okay, it has gone beyond that. Like regression is easy to interpret regression, but it's less flexible. If you're conversant with classical regression, you know that it's loaded with a lot of assumptions, multicollinearity, linearity, homozygosity, and the rest of them. A lot of, assumptions are there, trying to, limit the scope of what it can do. But the machine learning is very powerful. But the only catch there is loaded with what we call the black box. Okay? It's loaded with what we call the black box. That's the contrast there. The black box describes a model where you can see the inputs, you see the output, but the internal decision-making process is a bit invisible and a bit complex. So some people are like, okay, this is what machine learning is predicting. How did that happen? So that brings us to the explainable artificial intelligence aspect. So that's what is boosting the machine learning now. This provides tools to answer questions like, which features are most important in this prediction, in this model? How did the model make this specific prediction? What happens is if a variable changes? And the explainable AI uses tools like the Sharp, the Dallas, the Lime. But for this work, I think I did I used the Sharp and the Dallas, okay, when we go to the hands-on. Okay, so explainable AI does answer these questions. It more like tries to open that black box where the workings of the machine learning is. It tries to understand how machine learning models make their decisions. and then helps interpret predictions without really sacrificing the performance of the model. Okay, so this is the contrast. In classical regression, we model relationships. In machine learning, we optimize predictions. And then in classical regression, there are assumptions, a lot of them. But in machine learning, is data-driven patterns that we follow. We see a lot of patterns of the data, and the model goes according to the pattern that is given from the data. Now, in classical regression, we have to interpret the coefficients. In machine learning, we explain the predictions using the explainable AI. Classical regression focuses on inference. Inference, you take a sample, you do everything, then you generalize your results to the population. But in machine learning, we focus on performance, accuracy, and interpretation. Now, from machine learning, we'll move to the deployment mindset. Deployment is turning a trend model into a usable tool in the real world, because what machine learning does is it gets a data set, it splits it into the training data and the test data. Now, the training data is what we use to learn the behavior and the patterns of the data, and then we create our model. And then the test data is what we use to validate the model. If the model is validated where the performance matrices have been seen and is very good, then we can move beyond that and make this trend model to be reusable in the real world. There are common ways that trend models are deployed. You can see a lot of them in web application, like embedded model in a website, in application programming interface, when model is hosted on a server where other applications send data and they receive predictions. We also have the batch processing, where model runs on a large data set at intervals. We also have the embedded systems, where models run inside devices. The most common is actually the API, where these models are hosted and online, and the people try to, send in their data to receive their predictions. So we have moved from the classical regression to machine learning with explainable AI, where interpretability is very okay. Okay, so in summary, in machine learning, we have the training, you have the testing, you have the new data. The training is where you learn your data, and then the test part is where the model that's been trained is validated. And then the new data is the deployment part, the application of this trend model into the real life situation. So the essence is to trust the trend model enough based on its performance matrices and to use it for real world applications. So this is where we are. So now the next phase of this class is to move us to the hands-on. This is an R group, so we're going to use R in order to have a feel of how machine learning works, how these models are trained, and how they are tested, and how we can check for their performances and see what is going on. So I will now go to the R. So I'm going to remove this, and then I'm going to share my R. I'm going to use R Studio in this class. I hope most of us are conversant with R. I might not go through the nitty-gritty of how the types of data R uses and all that. So I'm going to share my R Studio now. So
We are with you, Prof.
Okay. Just a minute.
All right.
Okay. Oh, are you seeing it?
No, we cannot see it. We can only see your slide. You have to drop the slide before you can share.
Okay, let me drop my slide. Okay, can you see it now?
No, we can't see it.
Yeah, we can see it now.
You can see it, okay.
Yes.
Yeah, yes, I can see it now.
Okay, that's
Okay.
better. So this is Arrow Studio. This Arrow Studio, you can see there are 4 windows. We have our console, we have our script window, and the other 2 windows. I don't want to go into that. So today, we are going to, our case study will be on diabetes data. Is a data that is in a package called the ML Bench package in R. Okay, so what the first thing you do when you want to start working on any data is to first of all understand the data you're working with. We are working with this data set from ML Bench. The name of the data is Pima Indians Diabetes Data Set. Is a classical binary classification data set in the sense that it has some features which we call the predictor variables, and then it has the target variable, which is the diabetes. And diabetes is the outcome. And the outcome is binary in the sense that are you positive to diabetes or not positive to diabetes? So there are 2 outcomes. That's why it's a classification, a classical classification problem. You can also have classification that are more than binary, but that's not what we're doing today. We are looking at just a binary classification. Now, our data set has 9 variables with 1 target, which is the outcome. Now, these features are 8 of them, and they are all numeric except our target, which is our status of diabetes. Okay. Now, in carrying out machine learning, there are a lot of packages that you need. I've already installed the packages, but you can see how you can install it in the script window. Okay, you see all the packages there. You have the read Excel. That's what you use when you want to import data from Excel. But I'm not going to go into all that. So what I'm going to do, the first thing I'm going to do is to call up these packages that we need. When you install your packages, when you want to work with them, you want to use the functions in these packages, you're going to call it up using the library function. So all of them, I'm going to highlight the whole library that I'm using. And I'm going to run them so that I can be able to use the functions in them. So I click on run. So it's going to load all these packages so that I can be able to use them. Now, as I said earlier, the data we are using is a Pima Indians diabetes data. It's inbuilt in the ML Bench package. So because it's there, I don't need to import it from anywhere. All I need to do is to use the data function and then call up that particular data that I need. Okay, so my cursor is on it and I'll say run. So it just brings in the data for me. So we can view it. We can view this data. Just a minute. Some people are waiting, so we can view this data. I click on view. So that is the data before us. We have pregnancy, glucose, pressure, and the rest of them. Let me give a little explanation of these features. Pregnancy is for the number of pregnancies the individual have had. We have glucose, the level of glucose. This pressure is actually the diastolic blood pressure. Then you have the triceps, you have insulin, we know that. This mass here is the BMI, the body mass index. We have the pedigree, that's the story, the person's family history. You know, there's a probability of, there's a way they calculated it, and you have age, and then we have diabetes. You can see the diabetes, you see positive, negative, and all that. So these are the variables that we have. Okay, now we look at the structure of the data using the str function. So I'll look at the structure of the data. So looking at the structure, you can see at the console, whatever you do on the script window brings the result down on the console. The console is the left down window where I'm moving my cursor on. I hope you can see that. So this is data, is showing us the structure of this data. It's telling us it's a data frame. It has 768 observations with 9 variables. All the variables you can see, it means they're all numeric variables. But the diabetes is a factor variable. By factor, it means it's categorical, it's categorized, yes or no. For this instance, it's negative or positive. Now, for us to start, I like setting a seed helps for reproducibility so that it can be reproduced again when you have a seed. So I set my seed at 2.212. You can use any number. Now, the next thing you're going to do when you're running any form of analysis is to clean up your data and get it ready for analysis. If you look at this data, when we called it up, you can see a lot of zeros. You can see that, like the diastolic blood pressure, you can see 0. A normal human being cannot have a diastolic blood pressure of 0. You can also see insulin 000, which is not possible. It's only a dead person that can have zeros. So these are the things, you just look at your data, body mass index of 0, that's not possible. So when you look at all these things, you begin to reason, why are these zeros? That means they represent missing values. Values are supposed to be there, but because the values are not there, their zeros are all imputed. But in pregnancy, there are zeros in pregnancy, but we are going to ignore the one of pregnancy because it's the number of pregnancies the patient may have had. And you can get somebody that have not had any pregnancy, and that will represent 0. Okay? So we are going to, first of all, treat these missing values because machine learning does not tolerate missing values. Okay, so we check for the columns that have missing values using, the cosum function. So I run this. Dr. Tim, please help me with the people waiting in the waiting room so that it can come in. So I'll run to find out the values. Wait, what's happened here? Okay. I think I worked on it yesterday, so you may have just, okay, what I'm going to do, because I really want you to see the features that have missing values in it, so I can get to this point. So I'm going to do something. So this is my data. They have missing values. So I go back and I want to rename this. So I'll use a small letter P. I use a small letter P and run it. So let me see. I want to see the head part of this data. So, okay. So I will run this. So I can see the head part, so it's still having zeros. Okay, so we are going to work with this. So in order to see the columns that have missing values, okay, now it's showing us very well. You can see pregnancy is there, glucose, pressure, tricep, insulin, and mass. But pedigree has 0, so there's no missing value here. Age, there's no missing value. Diabetes, there's no missing values. That's why you're seeing 0, 0. But these ones are the ones that have missing values. And I said earlier, We are going to ignore pregnancy because there could be people that have not gotten pregnant before. So pregnancy is not going to be part of the features that we are going to deal with in terms of the missing values. Now, R does not represent 0 as a missing value. It will see it as a number. So the first thing we are going to do is to turn those zeros into what R can recognize, which is NA, okay, not available. So what we're going to do now is we name these columns that have missing values. We name it columns with 0, okay, so that we can be able to work with it. So we have named it. Now we are going to replace all those zeros with NA, okay? That's the code for that, and we run it, okay? So now we are going to check whether these zeros have been replaced with, okay, I need to change, we are working with, I need to check that's okay. So I want to look at the head, make sure it has been turned into what we want it to be. So, okay, I didn't change the P to small letter, so it's still working with, the capital letter P. Remember what happened? I needed to do it so that you can see. Okay, so I've changed it to that. So let's see the head to be sure that he has replaced it with the head. It has replaced. I think I've already done the capital P, so it didn't show us this part. So let's go ahead and check for outliers. Now there are missing values there. Now there are missing values. We want to find out, okay, this is why I'm having issues. So I will run this again. Okay, and then, okay. It's still showing me P values because I've already run. I don't want to redo it again. So what we're going to do in order to impute those missing values, this, as you can see here, is already been imputed, but I want to guide you through the process of imputing it. So when you check for the outliers, okay, that's the first thing. When you check for outliers, those that have outliers, we use the median imputation. But those that do not have outliers will use the mean imputation. Okay, so we name these columns. Okay, and then in order to do that, we turn it into a long format so that it can be able to plot, because we want to plot the box plot to see the ones that have outliers and the ones that do not have outliers. I hope I've run it before the. Okay, so you can see there are outliers on 1, 2, 3, 4, except for the glucose. So because of those outliers, we are going to do median imputation for those 4, the mass, the pressure, the triceps. So we'll go ahead and do the median imputation. Okay, we also do mean imputation for just glucose. Okay, so let's confirm whether we still have missing columns. So we can see there are no more missing columns. There are no more missing values among these columns. So we are good to go. The whole missing values have been imputed. The one that had outliers, we use the median imputation. The ones that do not have outliers, we use the mean imputation. It's always good to also check for duplicates. Sometimes when you're working, some things can run and you have duplicates. So you can see false, that means there are no duplicated rows. Okay, so you can use also the scheme function to actually see how these variables are. So this scheme actually shows you, it's more like doing a summary. It gives you, it gives you the number of variables, like you see, the number of negative, the number of positive. It gives you the mean, the standard deviation, the first quarter, interquarter, all those things. It comes, and even a brief description of the histogram, you can see it there. So sometimes it's always good to look at these things. It helps you to, work. Now, the next thing we want to do is we want to check for correlation. Why we are doing that is because we are going to use a explainable AI to interpret. When there is correlation between variables, okay, it tends to influence interpretability. Why? Because if two variables are correlated, their importance, because they are correlated, their importance are like shared between them. So you won't really see the true importance of each of them because it's been shared between them. So it's always good to check for correlation so that if there's severe correlation, you can actually drop one variable so that you can actually be able to see the influence of the other variable very well. So we select the numeric variables from the data set. Okay, we select the numeric variables and we call it the P1 diabetes, okay? So, and then we compute the correlation metrics, okay? Now we can view the correlation metrics, but it's always better to look at it through a plot. See the correlation metrics, you can see the maximum there is about 0.54, which is not really severe correlation, but let's look at it in a plot. It will be clearer for us, okay? So you can see it in this plot, So you can see from this plot that there's no really serious correlation. The maximum correlation there, I think, is between maybe pregnancy and age, okay? If you see this pregnancy, it moved to age, you can see that the blueness is a bit darker than the rest, but you can see the rest are very faint, so we are so good to go that there's no problem of multicollinearity. Then another issue that we usually face in machine learning, especially in classification, is the problem of imbalance. When you have an imbalance means, like in this classification now, positive and negative responses. If the negative responses is so far away and the positive responses is very, very small, maybe like 6:1. So when you see such a ratio, is an imbalanced distribution and it affects machine learning. So when such happens, as a way machine learning corrects that, you use maybe like function like smooth to balance it by creating how do I put it, like more like dummy outcomes so that it can balance it, but those dummy outcomes do not really have an impact. Okay, so that it can balance in the prediction. If not, the model will tend towards the one that is more, you understand, biasing the outcome prediction. So in order to do that, it's always good to check for imbalance in your data set. So the first thing you do is turn it into a table, and then you run that to see the balance. So we run this, and we can see that our imbalance ratio is 2:1. That means it's 2:1. The negative is 2, the positive is 1. So 2:1 is not really a bad imbalance. So it's not a problem. So we can move ahead and move into the machine learning models proper. So as I told you earlier, the first thing you do is to split the data. So we're going to use the create data partition to split our data into the trained data and the test data. I use the proportion of 80% for the train and 20% for the test data. So that's what we basically did here. So you can see the P is proportion of 80 to that. So we run We run it. Okay, so we have our trend data and we have our test data. Okay, so let's check out the number of rows of our trend and our test data. So you can see our trend data, the 80% gave us 615, rows, and then the test data we have 153. Now we want to tell the model which outcome we care about most. Okay, so our interest is the presence of the disease, which is positive. So we are going to do that, but we do it differently. We do for trend and we do for test. Now that we have separated it, the trend and the test, anything we do, we are going to do for test and we do for trend so that we don't have what we call data leakage, So we don't combine the trend and the test so that the data does not leak, so that the whole model learns everything before you even try to validate your trend model. So we do this. Okay, and then we get the target from the test and the trend. So we have the target, our target is diabetes from the test data and then from the trend data. Okay, so we also, the way we got our target, we also get the features. So we separate, we also collect our features from the data. The features for the trend and that for the test. So now we have gone to, the data has been split. So we are going to do what we call cross-validation. We are trying to tell the model how it's going to validate. They do the cross-validation. So when the model is being trained, sometimes if you engage the validation process, the cross-validation process, there are different methods. You can have the CV, but the one I'm using here is a repeated CV. What it does, and I told you it breaks, I told you the number is 3. So it's going to break as it's training, it breaks the data into 3 parts, use 1 to validate and use 3, for control. And it's going to repeat it twice. That's where you have a repeat for 2. So if you're using another form of cross-validation, you might not really need to repeat because this one is repeated CV. That's why we have to put value for the repeat. So we are going to run this, our cross-validation. So then the first model we are going to look at is the machine learning logistic regression. It doesn't operate like the classical logistic regression. So we call our model LG. Okay. Now we use the function train. So our target is diabetes and we use our data. Remember, when you're training your model, you're using the train data. When you have finished training, then you can use the test, okay, to validate what you've done. And the method we are using in the logistic regression is a GLM, generalized linear model method. Okay, so we run this. We run our model. Okay, and then we're going to predict now using the test set. And our test is the test PD. Okay, now we're going to include probability type as probability. Why? Because I want us to look at the receiver operating characteristics, where we are going to plot the AUC, which is the area under the curve. So in order to do that, it needs the probability. So that's why we are doing that. So it's going to get the object and then it's going to plot it and give us the value. So okay, let me plot it, then I will explain. Okay, so we can see the ROC curve, okay, and the value of the area under the curve is 0.84. So looking at this graph now, the plot here, you can see this diagonal line. This diagonal line is the point is 0.5 point, where anything that the model does is out of random, that is randomly generated, the result is randomly gotten, which is not a good one. Okay, so anything below this point is not good, but anyone that goes towards the left-hand side and moving towards the upside of it is actually a good model. So we can see the value of our area under the curve is 0.804. What this basically tells us is it gives us the how do I put it now? The ability of the model to distinguish between the positive and the negative values, the positive and negative outcome. Okay, you can see on the y-axis is sensitivity. On the x-axis is specificity. Now, sensitivity is the ability or the proportion of actual positives that are correctly identified. It gives you that proportion. While specificity gives us the proportion of actual negatives that we are correctly identified. Okay? But all in all, it's been able to give us a very pretty good value of 0.808 for our logistic regression. That is telling us that the model is good and it has the ability to distinguish between diseases and no disease, status. So we move ahead. I need to move this. Okay, let me remove this. Okay, so we have seen our area under the curve. Now we are going to evaluate now with the confusion matrix. As the name is a table that is used to evaluate performance of a classification model by comparing the predicted levels to the true level. Okay, I will explain that as we do this. So now, in order to do that, we are going to predict again. But in this case now, the confusion matrix does not use probability, it uses actual values. So that's why we can't use the formal prediction we use to plot the ROC plot. So we are going to predict again, but now without the probability. That's why you can't see type probability on this one. So we predict and then we create our confusion matrix and we print it. So this is our confusion matrix. Okay? Confusion matrix. I'm going to show you the plot, but this confusion matrix, you see what is showing us here? Okay? When I plot it, I will now explain certain things to you. You can see positive here and negative here. Negative onto negative, it shows us that this model was able to rightly predict 91 individuals as not having the disease condition. Okay? And here is, it was able, okay, let me just plot it. So let's plot it. Okay, this is our plot. Okay, so this is our plot. You can see the green parts are the right predictions. Okay, this one are those that do not have the disease, and they were rightly predicted that they do not have the disease. Now, these ones are the ones that have the disease, and they were rightly predicted of having the disease. Now, these ones are the ones that, here are the ones that have the disease, but they were wrongly predicted of having the disease. Okay, they have the disease and they were wrongly predicted of not having the disease. These ones, they do not have the disease, but they were wrongly predicted as having the disease. So that's what that plot is showing us. Now, if you come here, you can see the accuracy of the prediction is 0.7. Okay, you can see the sensitivity value, the specificity value. You can see, yeah, it has the ability to rightly predict, okay, the negative, okay, but for the positive, is giving you 39%. So he failed in rightly predicting the positives, but did very well in predicting the negatives. Okay, now we are going to go to the feature importance. Why I'm taking time to do this is when I'm doing the other ones, the other models, I will run through them and then go to the comparison aspect. So that's why I'm taking time, because we don't really have so much time. Our time is already running. So we are going to plot the feature importance. So we use this to get the feature importance. Okay, we run this. Okay, so this is the feature importance. From this, you can see that the feature that contributed more, that is very important to this particular prediction, is the glucose, followed by the mass, the pedigree, and, it goes down, to the tricep that doesn't really have any contribution. So let's plot it so that we can see it very well. So this is my code. So I will run this. Okay. So we can see the feature importance plotted. So it's showing us from glucose onto the list how important they were in predicting this logistic model. So the most important is the glucose, followed by the mass and the pedigree. Okay, and then it tapers down. Okay, so now we've been able to see the accuracy of this prediction. Now we're going to move to the explainability of what we just saw in the machine learning aspect. So we are going to use both the sharply additive explanation. That's actually what sharp means. And then after that, we are going to use the $sharp. Okay, I said here the sharply value helps in machine learning to explain how each feature contributes to the prediction made by the machine. Okay, it provides a way to fairly distribute the credit for the model's output across all input features. Okay, we're also going to visualize it. Okay, you can understand not only which feature are important, but also how specific the feature values that are driving predictions for this individual, because we are going to use individual, we're going to pick individuals and see how they predict the features help in the predictions. That's how good explainable AI is. So we also set a seed in this for you to be able to reproduce it again. And now we create our predictor for that particular model. Okay. Okay, I think my model was capital. Let me be sure because of the small adjustments I just made. Okay, model is good to go. So we run this. Then we select a single instance. What it means in our test data, we want to pick one individual and see how the features, the variables that are measured from this individual, how it helps in prediction. The values, which one added to the prediction, which one removed from it. So we are picking row number 6 of the test data. So if I open the test data now, we are going to look at the 6th person. That's why this 6 is here. Okay, that's our interest. So we pick that individual and then we compute the sharp values for it. Okay, so for this particular individual, this is the sharp value. Okay, we can see how that individual has come up, okay? You can see the average prediction for this is 0.28, okay? So this is the difference, the average prediction difference. So it moved up by this particular prediction. Now, you look at the number of, okay? So we can see the phi is actually the contribution to the prediction. The phi is actually the contribution. You can see that is only this that contributed to the prediction tilting towards the positive. All these ones, all these negative values are showing us that they all contributed towards the prediction going towards the negative, not the positive, because the prediction predicted that this particular individual is positive, okay? That's the prediction. But now this is the contribution. This pregnancy, glucose, and all that gave a negative, they impacted negatively to that prediction. Why the body mass index, helped increase the prediction towards the positive. That's actually what this is telling us. So we can look at the plots. So we look at the plots, okay? So we look at the plots. This is how I'm trying to move this into and fro so it doesn't disturb. Okay. So these are the ones. This is only the one that improved the prediction for that patient to be predicted as positive. Then all these ones reduce that prediction, and they are tilting towards the individual not being diabetic. You can see glucose of 118 is actually low. You can see no pregnancy at all, okay? So all these things, and the diastolic blood pressure 84, all these ones, they are pulling the prediction towards, this person, the prediction should tilt towards the person not being diabetic. But the body mass index is actually pulling it towards, the person being positive. This is just the same thing with this, so this is going towards the negative, this is going towards the positive. Okay, so now we have seen the plot. Now, since logistic regression represents two outcomes, column 1 and column 0. I want to compute get what we call the kernel sharp. Why this is not really, you mustn't do this, but I wanted to do this so that we can see some beautiful graphs that we can use, assuming you're going for a publication. Okay, it's always good to put such interesting plots in your work to make it interesting. So we are using I want to create the kernel sharp. The first thing is to create a function. When you create this function, you now use it to create your kernel sharp. This usually takes a little while to create a kernel sharp. It takes a little while. Some models, it takes up to 6-7 minutes, like the SVM. So I'm not going to do that for SVM. It takes a long time for this kernel sharp to be created. It's going to take us up to 100% before we can be able to plot this B sharp. The plot is really very nice, and you can see how it's looking. So let's give it a few more minutes, and it will go there, and then we can now plot this. Okay, yeah, we're almost there, so that we can be able to run okay. The kernel sharp has been created, so we can plot it, and you will see a beautiful graph by the side. So you can see this beautiful plot by the side. It's actually showing you the way the features, help in the prediction. You see this yellow part is the high part, this is the lower part. So you can see the purple line is that most of them are on the negative side, telling you that when the values are low, it tilts towards prediction of no disease. But when the yellow parts are high, when they are on this part, is pushing you can see the positive side is pulling the prediction towards predicting the presence of the disease condition. Okay, so that's what the B sharp does for us. Now, so let's move ahead to now go to our dollars. I told you we are going to look at the sharp which we have just done. Now we are going to look at the dollars sharp. So the first thing you do is to create the dollars explainer. Okay, so we create that for the logistic regression, and then we do a prediction using the particular instance. Remember, we looked at the sixth patient from the text data. We're also still using that for the dollars here. So we run this. Okay, so we now plot it. Okay, this is another interesting one. So we have plotted the dollar sharp. This is now showing us the contribution that each of the feature is contributing to the prediction. Now, this is mass. Those on the green are the ones pulling it towards increasing the prediction of disease, while the red ones are pulling to the negative, pulling it towards the prediction of no disease. Okay, so now we have seen this. Now let's see how it's broken down. Okay, we use the predict part so that it can break this plot we are seeing to actually give you the numeric proportion of contribution of all these features. Okay, so I'm going to run this to do that. Okay, so this is how it's showing us the intercept. This is the prediction level when the features were not considered. Okay, it was at 0.295. Now we bring in the features. What are they contributing towards this prediction? Now the mass, you can see, is increasing this prediction by 0.245, which is quite high, and then the other ones are, there's another one is the pedigree is also pushing it to increase the prediction, while the rest are reducing the prediction. So at the end of it all, when these individual prediction powers are added and subtracted to the initial prediction power when there was no feature added, it brought us to 0.406. Okay? It brought us to 0.406. That means there's improvement in the prediction. That means these features had serious effect. It has increased the prediction power of this particular individual. Remember, we are looking at one individual. It's actually called local interpretability. That means we are interpreting it locally, going to individual by individual. So you can pick any person from the test data and you'll be able to know what the features of that person, how they contributed to the prediction of that particular person. Okay, assuming the person was predicted to be positive. Now you open it up, break it down, you will see which feature helped in increasing the prediction and those that reduce in that prediction. So that's the wonderful thing about dollars. Okay, so that is that for the logistic regression. Okay, now we have the random forest. Random forest is still the same process, but I'm going to run it through so that we can come to this part, and then we go to where we do a comparison of all these models. So I'm going into the random forest now. Okay, the random forest model. We create the model, we do our predictions, we plot our graph. So I'm going to be doing a whole lot of things together. So he has already plotted the ROC curve. and he has given us a curve under the area under the curve to be 0.806, which is also good. Now let's do our evaluation. We create the confusion matrix. We run the confusion matrix. Okay, you see how the prediction is. That has a little bit increase. Okay, it's been able to increase this, and then we also plot it. Okay, you can see the plot also. Okay, the feature importance is the next thing we are going to run. We're going to run it and we're going to plot it. So we're going to plot it and you can see the feature importance, the values and all that. So here we go ahead and go to our explainability. We set our seed for it. Okay, and we do all this. We do all this for the same individual. We do all that. We print our sharp value and we run it. It's also going to create our plot the way we did it before. Okay, so you can see in this one we have okay, so I'm running through it. You can see the sharp plot. Okay, the same thing with the B. I'm not going to go into the B's one because I think this one, the kernel sharp may take longer, but when you run this code, it's going to give you that beautiful plot where you see B swarms like that, showing you the ones, the house prediction and when to see that the increases the prediction of positive and all that. So let's go ahead and create our explainer for the Dallas sharp. Okay, that's where I'm running to. So we now still do the same local explanation for that same individual. I just wanted to use one individual for the whole. Then you can always do other individuals and see how that will pan out. Okay, so we do the breakdown plots. Okay, so you can see here. Okay, you can see that the individual, the features of this particular individual actually pull down the prediction. Okay, it actually pulled down the prediction of disease, pulling it towards the negative. You can see it reduced the moment the prediction was 0.7, but the moment these features came in, okay, the prediction for presence of disease, but the moment these variables, these features came in, it pulled it, reduced it, the prediction of positive, and reduced it drastically to 0.35. So it's pulling it towards predicting that this particular individual does not have the disease condition. So you can see the specific contribution of each of these features for that particular individual. Okay, so now that we are in a support vector machine model, the same way, we're going to run it through. Okay, we train the model for the SVM, and then we also plot and get our AUC. You can see the area under the curve is a bit reduced, 0.795, compared to the logistic and the random forest. Okay, so we'll go ahead and also do our confusion matrix and plot our confusion matrix. You can see, okay, even the number of well-identified positives, negative, has dropped from 90-something of the other models to 80-something. Okay, though the sensitivity increased compared to the other ones. You can see 0.43. The other ones were giving us 3-point-something, 0.3, and all the rest. So we also look at the feature importance. Okay, we look at the feature importance and also plot it. We look at it and we also plot our feature importance. Okay, so you can see the same plot. All of them are basically giving us the same glucose mass especially glucose and mass. For these three models we've done, you can see that the features that contributed most in the prediction is glucose and the BMI. And then age, and the other one was pedigree, the other one was, it changed, but the first two has been consistent for all the models that we have seen. So we go to Dallas, we set a seed for our Dallas, and then we go ahead to get our SVM so that we can get a sharp for it, and then we plot for that particular individual. Okay, so that is that for, you can see the plot, the ones that are helping us and the ones that are going against our reference. Remember, our reference is at the positive part. So anyone that is negative is pulling you towards a negative prediction. Anyone that is positive is pulling us towards the disease condition. So the B SWAM, I don't want to go into that because when we want to create the kernel shop, it's going to take us like 6-7 minutes. So I don't want to go into that. So the B SWAM for this, we will not see it. So let's create our explainer from Dallas so that we can look at individual contribution for any specific person that we pick. So this is our local explanation. We pick it up, we run it, our local explanation. Okay. So this is the plot. You can see the same mass, body mass index is actually a very good contributor to the prediction of the disease condition for this particular individual. We can see that being consistent in the two other models. This one is still telling us the same story. Okay, so now let's break down the prediction. Let's break down this prediction. Okay, we break down this prediction and we can see the individual contributions. You can see here there's an improvement. It's pulling us towards predicting disease condition because from the first on the intercept is 0.29. Okay, but now at the end of it all with the help of body mass index and the pedigree, okay, the history of this particular individual, he has increased the probability, the prediction power of the person being in that disease condition. So you can see it increased from 0.29 to this, and the major contributors is the body mass index and the pedigree of this particular individual, while the other ones were reducing it. So that's that for SVM. So that takes us to the SGBoost. So we still run SGBoost. SGBoost is a little bit more complex than the other one because it works with different trees. It's like the tree keeps increasing. Whatever mistake this level of nodes get, the next one corrects it and they move, and that's how it moves. That's why, well, like now it's running. There are a lot of trees, a lot of branches in SGBoost, okay? So most times it's always a better model, but we'll look at the endpoint and see which of the models actually did better for us. So this is our SGBoost. He has finished running. So we do our predictions and we run our ROC curve. So see our ROC curve, see the area under the curve is still high, 0.87. Now let's get our confusion matrix and see how that one also performs. So we get our confusion matrix and then we plot it. You can see there's an increase. Even the number of negatives the number of wrongly predicted individuals have also decreased. Okay, and then let's look at the feature importance and see the story that the individual features are telling us. Okay, so we plot that. So we can see from the plot, we are still having glucose and mass now with age. Okay, so glucose and mass are major contributors, very important in the prediction of this particular individual. Okay, we're not going to do the B SWAM, so we are going to We're going to skip that. Okay. And we're going to our dollars. Okay. So in order to do this, XGBoost works with matrices in creating the dollars. So that's why we started from converting all this into metrics before we can go ahead to create our dollars explainer. So we now create our explainer. Okay, it's been created, and we move ahead to get, okay, so we plot our sharp. Okay, so we can see the contributions. Okay, so we go to the individual comparison of this, or rather the breakdown of these predictions. Let's see whether, so you can see this particular individual, it reduced the prediction towards a positive, dropped it down to 0.4 because a lot of the features are pulling it towards prediction of the no disease condition. So it dropped the prediction power or the prediction level. Now we are going to compare the AIC values. Can look at the AIC values. Let's see how it looks. So you can see the area under the curve that is highest is the one from the XGBoost. The first one is logistic regression, random forest, SVM, and then the last one is XGBoost. So you can see that the XGBoost has more ability to distinguish between the positive and the negatives. Okay, so let's combine the plots. Let's combine the plots. It's a long code. Okay, after creating, first of all, you create a data frame. I created a data frame, and then we can now plot to see all four of them. Okay. You can see, okay, let's do the plot first. Okay, so we do this. Okay, so we can see the plots for the four of them. For the four of them, we can see that the logistic regression is a bit, they are very close when you see the values, but that's why they're a bit clustered, all together. It's even a bit difficult to separate which one is best among them, though it's XGBoost just a little, you can see, just a little. Okay. So now let's look at their comparison, their performance metrics comparison. So we do this. It's also a little bit long. So we run it off. Okay. So we do this. Okay. So this gives us a holistic performance table for all of them. So we can see the accuracy, the precision, the recall, F1 score, and which one is the last one? The AUC. Okay. So looking at all this, we can see that when we look at all this, when it comes to accuracy, XGBoost came out tops, even in precision. But in recall is same thing as sensitivity. We can see that the random forest did better. You can see the F5 score and then the area under the curve. XGBoost still outperformed the other models in this model prediction comparison. So I think I was able to do the 1 hour, 30 minutes that was given to me. So, I think we've been able to, okay, I think I did let's look at the comparison of the confusion metrics. Okay, let's run this. Okay, so this is a comparison of all the models. Okay, and we can see okay, that SGBoss actually correctly predicted 93 people that are not negative to actually not be negative, you know? Okay, so the major thing here is actually this diagonal part, okay? This is rightly predicted, you're negative, you're predicted negative, all these red ones. This is, you are positive, you are rightly predicted positive, this, and this. But when it comes to this, the down part, and also the upper part, this upper part is, you are positive for the disease, and you were told that you did not have the disease. You know, that is actually a very big problem. This is like a type 1 error. You know, there's a disease condition. No, this is like type 2 error, yeah. There's a disease condition, which is positive, and you were told that you are negative, and you go home with a disease condition. That's actually a very serious issue, okay? And the SGBoss was able to get 7 for that, okay? Okay, so this is the actual class, and this is the predicted class. We are predicted. So from all this, I think we can conclude here that SGBoss, though not in all the performance matrices, but we actually did better than most of it. So I think I've come to the end of the class.
Okay, that's so nice. Thank you very much, Prof. You have done well. I've received some messages in my private box and also in the meeting here. So you can see some users, some listeners clapping for you. Some are giving you love stickers and so on and so forth. That shows that you have performed excellently well. Thank you very much, Professor. On this note, I would like to invite audience, if there are any questions that they want to ask. Probably there are 1 or 2 things that they want Professor to tell you more about what she has explained before. So questions time, please. If you have any question, please, you are free to unmute yourself and make a signal, then we will allow you to talk. Thank you, Dr. Jima from Kwara State, Ilorin. Thank you. Thank you, Dr. Jima. Thank you very much. Dr. Jima from Alikiba University, Ilorin. Thank you. Thank you. Faith Adiyemi, I can see your message. Thank you so much, Prof. Faith Adiyemi from Equatorial Guinea. Thank you very much. Many people attend this meeting from different sectors of the world. So, if there's any question, please let us have the question. There is a question in the question box, which I've already answered on behalf of Prof. Somebody asked that, okay, there's one doctor or professor, Joshua Jato. He said, Dr. Maureen, thank you so much for the presentation, so helpful. Well, I would like to just quickly adjust that statement. This is a professor, not a doctor. So please, she's a professor. So, and the second thing she asked is, please, I want to know if the R can also be used for lightweight CNN. And also, another question she has was that, please, Dr. Maureen, hope that the recorded video will be shared later. Thanks. Well, I've answered the question, that question number 2, that's one comment. Yes, the R can be used to implement lightweight convolutional neural networks, CNN. However, the practical reality is that R serves mainly as a high-level interface to deep learning backends, particularly TensorFlow and Keras. So R can be used to do that. In the area of recorded video and all those stuff, we will share our material with you. Recorded video, the material, even the code. I'm sure the Prof will share the code with me so that I can share with our participants. We'll share all this material with you free of charge. But our certificates, if anybody wants certificates for this preparation, a certificate will cost you a token amount of money of 5,000 naira. but all the recordings, all the materials, and every other thing will be shared free of charge to all the participants. Thank you. Is there any
Okay, I
other?
want to add something. I
Okay,
want to say something.
okay,
Okay,
Prof.
when the confusion matrix, if you look at it, there's actual class and then there's predicted class. That's how you interpret it without so much confusion. Okay, so you see, this actual class is actually the class the person has, but this is the predicted value. So the worst case scenario is for instance, the person's class is actually positive, okay, and the person was predicted negative. That is this part, okay, that is this part, and this part. For instance, for the prediction of that one, you can see that the rainforest actually dropped the number of wrongly predicted the severe ones. Okay, so it's 23, while SG Boss is 31. That's like the type 2 error I was talking about. Okay, but this one and this one and this one is the type 1 error. You know, type 2 error and type 1 error, type 2 is more severe. Okay, so these ones they are negative, but they were predicted to be positive. So it's not really a problem because the person is already negative. But these heavy ones that are negative, that are positive, and they were predicted to be negative, they are the serious ones. So it's always very important to bring down these particular numbers, this particular 31, 23, 32, and 30. So that, I think I didn't explain it well before. I said, let me just chip in that. Thank you.
Right, that's so nice. I think we still have some other questions that people ask in the group, in this meeting. So, I would like to quickly talk about. So, we have one Mrs. Sister Joy Oyalade. You say you want to ask a question too?
Me. Yes,
Okay,
yes.
go ahead, please.
Prof, good morning, good afternoon, Mark. Thanks for the brilliant presentation. Please, I want to know the package used to present this data. Is it for the machine learning? I want to know the package you use. Is it R package or Python? I want to know the package you use.
It's R that I use, R
package.
statistical.
That's what you use
It's
for the
R
machine
Studio.
learning.
Yes. Are you
You
hearing
use
me?
for the machine learning. I'm
And
hearing
it's
you,
not
ma.
Python. Okay, it's not Python that we use. We use R.
R. Okay, for the
Yes.
machine learning.
Learning. Yes.
Okay, thank
Everything
you.
we
Thank
did
you,
here
ma.
was in R. Okay.
R package. Thank you, ma.
Yeah.
Okay, maybe to buttress what Prof has just said. This program, this event currently is being organized by Osun R User Group, Nigeria. So we can only try to promote R usage when we are promoting events under Osun R User Group. We can't be promoting any other software under this particular section. So Prof has used R throughout the calculation, the computations. So, and I think with that, wanting to just have it in mind that you go online, if you want to have R Studio or R package, go online, just type R Studio setup on your Google or your browser. It will come out. The latest version will come out. And from there, you can install into your machine. That is how to get it. Somebody asked a question about how to get the package. That's why I'm asking that area. So another question is from Dr. Phillips. Dr. Phillips is from South Africa University. Thank you, Prof. How can we get this software? And that's what I've answered. How can we consult for further inquiry? Thank you from Phillips, University of South Africa. Well, I've told you that the way you can get the software has been already answered. And to consult further, probably you can get in touch with me, and I will see the permission of the professor to give you our number or our email if and only if she wants that. So some of us came in late. Somebody said some of us came in late. Which platform can we be used for sharing the material that I can access? Anyway, let me quickly share the WhatsApp group that you can join. Our WhatsApp group that you can join on these meeting notes now, so you can see the WhatsApp group to join. But to get the materials, it has to be via email. The email you have used to register, that is where you are going to get the material. You can't get the material via any other means than the email. So because you have used email to register with us. So let me quickly send you the WhatsApp group where you can just join us for the or just see our further meetings, further things. So is there another question, please? Any other question, please? If there are other questions, please let us know so that we can address them. And if there is no question, I think we'll need to probably call it a day. But let's wait for next 1 minute. Yes, another question. I will share the link now with you now here now. Just 1 minute for me to share the link, please. So, Prof, do you see have something to say, probably to encourage us, or probably to see something? How can one join Osun R User Group? I will share the group now, the group link. Please, sir, I still have another question for Prof. Okay, please go ahead, Madam Oyalade. Oyalade. Sister Joy Oyalade, you said you still have another question for Prof. Are you there? Are you there?
Maybe you can unmute her. Maybe she can't unmute herself.
I have to look for her and look for where she is. I've shared you the link where you can join the WhatsApp group. Okay. Ogunjobi Olatoye, you have a question? I can see your answer.
Yes, my question speaks to. Thank you very much, Prof, for this insightful presentation. I wanted you to speak more about the cross validation that was done. I saw some cross validation. Maybe you can share more light on that cross validation, especially when you were talking about those imbalances, data imbalances, and the approach to them. Thank you.
Okay, I talked about data imbalance. That's talking about the classification. Okay, when you have the positive and the negative responses, when the ratio between the two is too much, like you have 4:1, 5:1, you can see that the model will tilt towards predicting the one with higher values. That's what it usually does. So the imbalance is a way of balancing both so that the model will not be biased and tilt towards the one that has more outcomes. So in order to do that, there are packages you use to balance it out by creating more like a dummy responses to balance it. But those dummy responses are not really the actual balances. So it's just to balance so that the model will not tilt towards the one that has higher outcome. So that's what we do. So you need to check the imbalance ratio, which we just checked, and we saw 2:1. That means because we saw that our negatives are more. It was 2:1, so we had like double the positive towards the negative. So it's not really a very severe case, so we can work with that. But when it starts to increase, there's need to introduce use a package to balance that imbalance so that you can get a good outcome. Then you talked about cross-validation. And I told you that in cross-validation, the machine tried to share the training data into the number of into the number that you want it to do. It uses like if it's 4, if the cross-validation number is 4, it uses 4 for training, and you use one part of that data for validating. Okay, and there are different methods. The one I used was repeated cross-validation. So what repeated cross-validation does, it will first of all do the depending on the number you feed it, it will share the training data into, if it's 3, I use 3, it will share it into 3, and you use 2 for the training, and you use one part of that data for the validation, and it will repeat it. I said I should repeat 2 times, so it will repeat that process, okay, so that you will get a particular control that we use in training the model. So I don't know whether that answered your question. Is
Yes.
that okay? That's Ogunjobi, right?
Yes,
Okay.
please.
Yeah, it's good to hear you, sir.
Yeah. So one last question is, how will you summarize explainable AI? Because I had a different view, but from your presentation, it seems it's deeper than I had initially thought. So how would you summarize? Based on your experience, how would you summarize explainable AI? Thank you.
Okay, explainable AI, there are different tools that are used. As I mentioned earlier, you have Sharp, you have the Dallas, you also have a Lion. But for this work, I just purposely use both the Sharp and the Dallas. What it does is it computes, okay, the predictive power of each of the features, okay, those that are contributing to the prediction of the preferred outcome. In this work, our preferred outcome is there is disease condition. So it breaks it down and gives individual features their predictive power. Some are removing from that prediction, some are adding to that prediction, which gives us the final predictive power, or whether the person is where the prediction is going to lie. For instance, if the prediction at the onset without any feature is like, there's one we saw was 0.73. Now, in that 0.73, we now saw that some features we are reducing that prediction, that prediction probability, and some features we are adding up to it. There are instances where you see that at the end of the prediction, the predictive power actually increased. Okay, that means the probability of tending towards the reference point, which is disease condition, is high. The predictive power increases towards that side. And when it reduces, that means the predictive power has reduced towards no disease condition. So that's what explainability does. He explains it very well so that you can see the contribution of each feature. Per individual, you can pick any individual. It also has there's also global interpretation, but the one I focused on in this work is the local interpretation, where you can pick an individual and it gives you the contribution of all the features for that particular individual, telling us why the person was predicted to be positive or why the person was predicted to be negative. Okay, so in the machine learning will tell you this person was predicted to be positive. Then explainable AI will now come and tell you why that person was predicted to be positive, because this feature did this feature did that, and at the end of it all, the person was predicted to be positive because of the individual contribution of those features for that particular individual. It's called a local interpretation because it's facing individuals. There's also a global interpretation where it will take a set of individuals. Maybe you can take from 1 to 100. Okay, and it also break it down for you. For this particular set of individuals, this is their main contribution, that made what so and so to be so and so. So I don't know. I hope I was able to explain it.
Excellent. Thank you very much. Thank you very much. God bless you, man. Thank you very much.
Amen.
Your time has changed.
Okay, Dr. Tim.
Yeah, thank you very much, Prof. You can see a lot of encomium, and also accolades. So that shows that you are a professor in that area. Thank you very much. We appreciate your coming your efforts, because it's not just these 2 hours or 1.5 hours that we have to appreciate. We have to appreciate the time you have taken to prepare the slide, to prepare the note, to put those things to practical, to ensure that the errors are not included, to ensure that these notes are perfectly okay. In fact, so we have to appreciate those hours, those time. So out of your busy schedule, you can still create time to attend to us. Thank you very much. On this note, I would like to call this meeting to an end. And I've shared the WhatsApp group of our Osun R User Group to this meeting here. So whoever has interest in that group can pick the link there and join us. And you can follow us from further activities that we have on the pipeline. This month alone, we arranged about 4 different webinars this month alone. So we have done 2 now. I think we have done 2, yes. And we have 2 in the front. Another one is coming on Sunday, this coming Sunday. While we begin, that Sunday will be just 2 hours training. And we have another one that will start on Monday also. That one is on Excel. And that one on Monday will take on like 5 days. Excel for 5 days. Excel from beginning to the end for 5 days to be in the night. So you will see the flyers in our groups. So thank you very much, Professor. We appreciate your time. Once again,
thank you very much.
Everybody is also appreciated for taking your time to be here with us. Good day and God bless you all. Thank you.
All right. Thank you, everybody. Thanks for coming in and joining. I appreciate that. Thank you.